in fact, because it's my second chance for talking here. And this work concerns some attempts to generalize Dirichlet problems or closed problems for the existence of graphs Riemannian manifolds with prescribed mean curvature, or even more general situations when the curvature is, for example, high-order mean curvatures or general functions of the principal curvatures of hypersurfaces embedded in Riemannian manifolds. First of all, you isolate some common features of Riemannian ambients in order to formulate and solve this kind of problems. The structure for that is to consider the existence of some special vector field, for example, a conformal Killing vector field, or for short, a Killing vector field. And we suppose that the distribution, which is orthogonal to this vector field in M, is integrable. And these leaves are leaves when I take leaf M, when I take domain or the leaf itself as the domain of definition of a function. So if you take the flow generated by y, given, for example, a function defined on M, the leaf, with values in some interval, you may consider if phi defines the flow of y, you may consider the hypersurface of the form Zx, x, where x is a general point in M. This is a graph, a Killing graph over M, the whole M, or a domain of M. So investigate conditions on Z in order to assure that this graph has prescribed curvature. So this is the general situation. Just for recall that y is a conformal Killing vector field if it satisfies this equation 1, or equivalently, the conformal Killing equation in terms of the covariant derivative of M. This is the flow generated by y, not necessarily complete. And I choose this leaf M as the initial conditions for this flow. So it corresponds to set t equals to 0. And this last expression is another way for expressing the fact that y is conformal. So the flow generated by y acts as a one-parameter family of conformal diffeomorphisms of M. The relationship between this lambda, which gives the conformal factor, and the whole, which appears in the conformal Killing equation, is given by that expression. This expression shows that the leaves, which are orthogonal to the flow, are in fact umbilic hypersurfaces of the ambient. So the leaves are natural examples of prescribed mean curvature. For example, in the case when y is closed, this means that the form associated to y by the metric is closed. In this case, for example, the leaves have a constant curvature. It's a trivial example of graphs corresponding to take constant values for the function z. This setting includes some interesting metrics. For example, we may consider the case when the vector field is isometric. So the flow generates one parameter family of isometries of the ambient. In this case, the metric is written as in the expression 4. In this case, you may consider, for example, the constant curvature matrix written as a double warped products. Another example, of course, are the Riemannian products. In this case, Y is a parallel vector field. Warped products, more generally. In this case, Y, this vector, this particular vector field Y, is a conformal Killing vector field. In the Euclidean case, for example, this corresponds to a family of homotheties around the origin. And again, space forms may be written as warped products for this particular choice of Xi. The first result obtained concerns graphs in warped products when the leaf M is a compact. So we take M times Y. Y may be a compact interval, open interval with compact closure, or even the real line. It's not important. The only assumption is that M is compact. And in this case, for warped products, the vector field is closed. And then the leaves have constant curvature. So you pick up a function Z, and then the graph is this hypersurface, as I put on the board before. And you consider also a region between two leaves. You take two instants, T minus, T plus. You consider this compact region between two leaves, two copies of M. So the question is to find a graph, to find a closed graph between two copies. This is the region M, T minus, T plus. And you ask about the existence of closed graphs in this region in such a way that this graph has prescribed a higher order mean curvature. So if you take the principal curvatures of the graph, you take a function of this vector and want to prescribe this function inside this part of M bar. This is the first problem. It's a closed problem without conditions on boundary or somewhat like that. So this results to be a nonlinear equation, and you put some conditions on the geometry in order to guarantee that this equation is elliptic. More generally, you may replace this HR, this higher order mean curvature, for a general function of the principal curvatures of the hypersurface, this general F. This F may be written in terms of the capital F, which is a function acting on bilinear forms. So you take the trace of B. B is the second bilinear form of the graph. You take the trace or the eigenvalues of B with respect to induced metric, and then you reduce this capital FB to the original F acting on the eigenvalues of the graph. And in this case, the general problem may be formulated like that. Capital F of B is equal to a prescribed function psi. Of course, you should impose some restrictions on psi, on the prescribed function, and on F. Not general F and psi work well, so you have to restrict somewhat the problem. The assumptions on F is that are that F is defined on a special cone, contain the positive cone in Rn and contain the origin of Rn. This is a guarding cone for assuring ellipticity for the problem. And F is symmetric with respect to interchanging positions of two lambdas. F is positive, concave function, and satisfies this condition. This condition says that the linearized operator of the capital F is elliptic. You have to control somewhat the derivatives of F, in the sense that you suppose that there exists some delta function with these properties. If you take the example of the higher order mean curvatures, or more properly, if you take these two examples, when R is greater than S, for these two examples, you may verify all these assumptions. You have to control F between two constants, and also to suppose something about the behavior of F when you approach the boundary of the cone. So our technical hypothesis in the general case, which mimics the case of the HR curvatures. As I say, these two examples are comprised in this general framework. So some previous results were obtained since the 80s, but all these results are formulated in the Euclidean space for graphs in Euclidean space. The first contributions after the classical ones by Oliker and Caffarelli, Nirenberg, Spruck, the first contributions were given by some joint work with Barbosa and Oliker, and after that by Yan Li and Vladimir Oliker concerning the case of elliptic ambient spaces. And after that, there is some result by Yan Li and Jean about the hyperbolic case. In parallel, Klaus Gerhardt and collaborators obtained results in this, about this problem using parabolic equations, some fluid techniques instead of the elliptic techniques I used here. The general result for arbitrary Riemannian manifolds or arbitrary warped products is that one, which supposes that M is compact. You take again this warped product with this warped function psi, and then you take this region between two leaves, two copies of M, and you suppose that the prescribed function psi satisfies these three conditions, 1, 2, and 3. These two first conditions concern are linked to the fact that these two copies of M are barriers to the problem. So if you consider these two assumptions, two first assumptions, you have automatically some height estimates for the graph. The third condition is somewhat more technical and is related to first order estimates. You may verify easily that these three conditions are natural adaptations of the conditions which appeared in the paper of Caffarelli, Nirenberg, and Spruck. So under these assumptions, you could you prove the existence of the closed graph inside this region, which prescribe mean curvature or general curvature F given by this function psi. Under this hypothesis on F, I showed before, the function, the equation is elliptic. The equation may be written like that. This general F acting on B, and B depends, of course, on the position of the graph. And the prescribed function psi depends also on this position. X is a general point on M. So, as I said before, the hypothesis concerns obtain C0 and C1 estimates for the graph, a priori estimates for the graph. And a piece of technology is that The functions are considered admissible if the vector of principal curvatures lie on this cone, this special cone, gamma. This result I showed may be found in these references. For the case, the second reference is about the case of mean curvature, and the first one for this general F. And the main tool for proving this result is the version of degree theory for dealing with full nonlinear equations, which was developed by Yang and Li. For applying this machinery, you consider this homotopy of problems. Instead of the original psi, you put this capital psi, and you consider this family indexed by S. And I perturb the original psi, putting on the right-hand side this phi times f. F is the function, the general function of curvatures, and k is the curvature of the leaf. So if you change the original problem, put in this additional parameter, you have a family, a homotopy of problems, and you apply the degree theory for this perturbation of the original problem. So choosing this function phi in the correct manner, you prove that there exists a unique solution for a trivial step for the problem. So the step which corresponds to finding a graph whose curvature is given by k, this first step has a unique solution, which corresponds to take the constant function equals to t0, where t0 is a point in the interval y when this phi is equal to 1. Besides that, you may show that the linearized operator around this particular solution is invertible. You have no invertibility for general graphs. You have kernel in general, because you have compactness. But in the special case of this particular solution, this particular leaf, you may guarantee that the linearized is invertible, in the sense that the coefficient, the independent coefficient is negative. So I have two informations: uniqueness of this particular solution and invertibility of the linearized problem about this particular solution. Then you may apply the degree theory. Just obtain now the a priori estimates. This is the third ingredient in order to apply the degree theory. So you work a little bit in order to obtain this C2 alpha estimate for solutions of all the steps of the problem. And these C2 alpha estimates produce fourth order estimates for the a priori solutions. Now in this, you may put the homotopy in this setting. So you have operator taking values on some bounded set in C4 alpha Hölder space. This open subset space, it's chosen in such a way that the solutions lie in some ball inside this O. So we have no solutions around the boundary of this domain. This is a typical situation for degree theoretical approach. And then use these two properties, these two familiar properties of degree, which are shared by this version of the theory. So this second step assures that the degree of the first step, the initial step, is the degree of the linearized operator, which is non-zero, because you have proved that this operator is an isomorphism. So you pass from 0 to 1, and then you obtain solutions for the original problem. The only thing to do is, of course, to obtain the estimates. The equation resembles like that. It's a full nonlinear equation for the case when r is greater than 1. In order to obtain estimates, you use these two magical functions, a kind of height function and support function. This theta is the angle between the normal of the graph and the Killing vector field. You combine these two functions. The gradients and Laplacians of these two functions are similar to the formula which appears in the Euclidean case. And then we combine this, putting all this information in this function, which interpolates between the height function and the Hessian function of the graph. B is the second fundamental form of the graph. And making some calculations around the maximum point of this function z, and using the formulas I showed before, you have an expression like that, which involves the fourth derivatives of the function z, or the second covariant derivatives of the b, the second bilinear form of the graph. This is calculated just choosing the maximum point of this test function I showed before. On the other hand, you may differentiate the equation twice. You have another expression for the fourth derivatives of z, and you combine these two expressions, changing the indices from a position to another. This involves, of course, taking in consideration some curvature terms. It's a kind of rich formula for the Hessian of the second fundamental form, and then combining this formula with the proper choice of h and beta, which appears in the test function, you are able to get a C2 estimate, and then C2 alpha, and after that C4 alpha estimates. So this gives a rough idea of the proof of the result about closed problem. Just for finishing, you present now the case when you consider not the leaf, the complete leaf as domain, but some open set on M, and this open set is supposed to have a regular boundary. So now you have a Dirichlet problem instead of a closed problem. So you get here this open subset, and now you have to prescribe, besides the curvature of the graph, the boundary of the graph. So you have now a Dirichlet problem. This was done for the case of mean curvature, for the quasi-linear case instead of the general case of general functions f. Of course, again, you have to estimate height and gradient, but the work is done when I have C1 estimates because of the Schauder theory for elliptic PDEs. So the barrier in this case are not these copies of M, but a Killing cylinder, which is a perturbation. Sorry, the Killing cylinder is just this barrier here. You take all the flow lines passing through the points of gamma, and you perturb this Killing cylinder a little bit in order to get a barrier, a sort of cone very, very near to the original cylinder. This works very well as barrier to this problem. So this K is the barrier, the Killing cylinder. Let me recall that the metric we are considering is like that. Now we have, again, the case of conformal Killing vector field, not necessarily closed. This is the terminology I used earlier. And the equation in the case of mean curvature is a divergence type equation, of course. You have perturbation terms with respect to the Euclidean equation concerning the acceleration of the flow lines and the fact that the flow lines are not geodesic. And the hypothesis now concerns relating the curvature of the graph and the curvature of the leaves. Essentially, suppose that the graph and the leaves have mean curvatures with opposite signs. In some sense, one of these are convex and another is concave in the mean. This condition permits to use the maximum principle. Okay. And the result is obtained in joint work with Max Deitzer. This assumption on the Ricci tensor permits to see that if you move this barrier in this direction, the mean curvature increases. So this is the correct behavior in order to get a barrier to the problem. Use this condition in some Riccat's equation in order to control the behavior of these moving cylinders. And the second condition is like a Serines type condition when the maximum value with the prescribed functional age coincides with the curvature of the cylinder. This is a limiting case for the curvature. Under these two hypotheses, you may assure the existence, you may prove the existence of a graph with prescribed curvature and boundary. For the case of closed graphs, you may improve somewhat the result, permitting that the mean curvature of the graph may be equal to the mean curvature of the cylinder. You have no strict inequality necessarily. So the technique is just to investigate in this behavior of these cylinders using Ricci tensor. So we have these distance levels for the killing cylinders. And if you put this condition in the Ricci tensor, you are sure that the mean curvature of the equidistant cylinder is greater than the mean curvature of the original cylinder. This is the main tool for proving the estimates for the gradient around the boundary of the graph and height estimates for the graph. Interior estimates for the graph are obtained by some sort of maximum principle for the gradient. Again, you use a homotopy of problems. You begin with the trivial problem, which is solved by the domain, and then you proceed with this family of problems indexed by tau. Tau equals to 1 corresponds to the original problem. And you use the continuity method under 3 steps, showing that the sets of values of tau for what I have a solution of the problem, this set is now empty. So you have a solution, a trivial solution for the case tau equals to 0. This set is open because you have maximum principle, which is assured by the geometric conditions on the mean curvatures of the graph and the leaf. And you have closeness of the interval y, the set y of solutions, because I have a priori estimates for the solutions. So you conclude the set y is the interval 0,1 itself. Just a brief idea of the proof. For having height estimates, you consider a perturbation of this function phi, which is given by the boundary term plus some function which has a very slope exponential graph. So this step assures the existence of these height estimates. If you take another test function, you may control the gradient around the boundary of the domain. And the final step is just to obtain a maximum principle for the gradient. obtain interior estimates, interior global estimates for the gradient. These three steps give the a priori estimates, and then you prove that this family of problem corresponds to the set 0, 1. So I depart from 0 with the trivial solution, I reach the final problem which corresponds to t equals to 1. So the estimates, the first order estimates are obtained again by linearizing the equation and changing derivatives using again some Ricci formula. So that's all. Thank you very much.
Are there questions?